Hey class, so this is lab 3 and today we're going over concepts on how to use counter, multiplexer, decoder, as well as the 7-segment display. This is the built-in display on the blackboard. My name is Bradley, and the problem statement is to implement a circuit that drives the time multiplex quad 7-segment display, which is this. Now, this is 4 individual displays, and each of these has a 7-segment that looks like this, where you can turn on or off each one of these segments to your desired output. And in this lab, we're going to be using counters, decoders, BCD to hex. This is to help us convert from binary to decimal, hexadecimal. Since we want to display the lowest value for each of these digit is going to be a 0. And after that, we will increment 1 by 1. So in hexadecimal, it would be 0, 1, 2, 3, until 9. And from 9, instead of going to 10, we're going to be going to the letter A, uppercase, and then B, C, D, E, and finally F. And that is going to be our N input. Since this is going to be from 0 to 15, we will have the 16-bit. And as for the switches down here, we're going to be using all 12 of these switches, as well as these 4 buttons here. And each of these digit is going to be broken up into 4. So each one of these digits here are going to be controlled by the 4 buttons here, as well as groups of 4s of these switches. And so this is the simulated waveform. And if I go back to this real quick, so the approach to solve this was to use different modules for the main design function. So the overall module is gonna be the display multiplexer, and of course some of these are given in the instructions. So we have a constant n for the local parameter, which is just a constant that we use, just so we don't have to change. If we were to go back and let's just say reuse this for another project, we can just change the value of n instead of going through line by line. There's a similar function in C where you can basically define your constant so you can use it over and over again. It should be, I believe, the same for Java. And then of course we want to avoid using latches, So we just gotta make sure that is not level triggered, but is edge triggered. In this case, we have the pause edge, and of course we're gonna be using the onboard clock, which is a crystal oscillator, and that's also necessary for the refresh rate. As of now, you could probably tell that the display is bright, and of course, how this would work is this would refresh really fast, right? But with our eyes, the human eyes can't actually detect how fast this actually flicker. So we think that these are high and bright and on all the times, but they're actually scanning and flickering. But then again, that doesn't really that's not a problem to us, because to our eyes this is on, right? So it fits with the requirement of the lab. And of course we have the cases for each of these inputs. So again, we have the four groups of how do you say, four groups of switches, as well as the very last group of four buttons. And again, we're gonna be using the counters and stuff to basically retain and cycle up or increment depending on the position of the switch. We can cycle from the lowest LSB to MSB, 0 to F, basically. And this is the constraint file for this lab. And then this is the test bench for the simulation. Oops, I forgot I ran it already, so could go back. Again, this was the result for the waveform simulation, which confirmed that this this code was working. But in a bit, we're gonna verify this on the actual board. So yeah, let's get down to it real quick. Again, like I said, we're gonna be using these switches as well as the buttons for the inputs, and you will be able to see that these 4 digits are gonna be incrementing, and the value is, I would put this in quotes, stored temporarily. So it's gonna look like this. If I were to turn this on, it would be a 1. And then since these are gonna be 1 1, the value is incremented to 3. You would have to add this, right? And if you were to turn this on, it would be a 7. So you would kind of see that this is working, because it's incrementing the values of the digits continuously. right? So this would display an F for that 16-bit. Since all 4 of these are high, 1, 1, 1, 1, thus F is going to be the value for our binary in 1, 1, 1, 1 in hexadecimal. And if we're going to do this again, all 8 are going to be on, so we would expect the LSB digits are going to be displaying F. Now let's turn on all 12 of these switches. We're going to see F again. And for the very last case, of course, I'm going to have to hold down all 4 switches for this value to be on, because if I let if I were to press the button just like this, it would just reset to 0 after I release the button. So of course, because that was how it was coded in the design module. So all 4 buttons are pressed. So the leftmost digit displays an F just like the other 3. And again, if I were to let this go, it would reset to 0. And that's about it. So we answered the first 4 questions. Now, what did I learn from this assignment was how to go from different modules to basically combine everything together. Like all of these codes had to work with the main design function. So it would give us an overall working bitstream file for the board. So this was very valuable because now I understand how to break this down into smaller modules and be able to connect everything together so that the overall design actually matches up with the given constraint as well as the test bench. So I'll be sure to keep this in my archive. If there's any good use for these code on the final project, then for sure this is a good learning opportunity to learn how to put everything together and reuse parts of the code as needed. So this is it. And then I'm gonna invite. Yeah. Okay. Thanks.